graphing derivatives, tangent lines, and second derivatives. So here we have a function f of x. You want to graph the derivative of it, f prime of x. So this is going to be 0. And remember that the derivative is just the slope of your function. So let's start from the left here. Our function is going upwards. It has a nice sharp positive slope because it's going up. On your derivative graph, you mark that by having a line here showing that your derivative is positive because it's above the x-axis at 0. Now at this part of the graph, the slope starts to get smaller and smaller until it hits 0 right here. On the derivative graph, you mark that by showing that the derivative gets closer and closer and hits 0. At the next part, the graph starts to go downward. Because it goes down, that is a negative slope. You mark that by having your derivative graph go under the x-axis. Now finally, at this part, the slope gets smoother and smoother and eventually returns to 0. So in that case, your derivative graph would go up to 0, and it may look something like this. Let's work on some simpler examples to get the fundamentals down. First, we have a straight red line here. When you have a straight, flat line, your slope is 0. When your slope is 0, that means your derivative graph is on the x-axis. And so since this is a straight line, the slope is always 0, then this derivative graph will always be on 0 here. This red line has a positive slope. It is going upwards. So you mark that on your derivative graph by having a line above the x-axis. The reason that this line is straight is because this slope is not changing. This slope is staying the same throughout this whole line, but it's still positive, and that's why we have a straight line above the x-axis. The same thing can be said about this one. This one has a negative slope. So we're going to have a straight line below the x-axis because it's negative, and this is a straight line here because this slope does not change. This slope is staying constant. And this right here, you can see we have two flat lines here. There's one up here, one down here, and each of them have a slope of 0. So how can we get a derivative graph on this? Since our slope is 0, we're going to have this line on our derivative graph. But keep in mind that because the function is discontinuous at this point right here, means it's also not differentiable. So we're going to have an open dot at this point in our derivative graph to show that at this point there is no slope that you can find, but at every other point there's a slope of 0. Here's another one. We have one straight line going up with a positive slope, and then a straight line going down with a negative slope. So our derivative graph is going to be split into two parts. There's this positive part, write that down here, and then this negative part, where it's going to go below the x-axis. Remember that there's a corner here, a sharp point in the function, so that means it's not differentiable. So on our derivative graph, you would have open dots here and here to show that at this x value, there is no slope. It's not differentiable. Now let's look at this one here. Let's analyze this graph first. At the left part, the slope is about 0. And the same thing with the right part. But right here, we have a vertical tangent line. When you have a vertical tangent line, the slope is said to be infinite. Which also means it does not exist, because infinity isn't an actual number. But how can we write this on a derivative graph? So see, the slope starts out at 0, and it starts to go up towards infinity because there's this vertical tangent line. And so you write that on the graph like this. Your slope starts at about 0 and goes up, approaching infinity. After it gets to this part, this infinite part, the slope starts to go down back to 0 again. Right here. You see that when there is a vertical tangent line, your derivative graph will have a vertical asymptote where the slope tries to reach infinity. It approaches infinity. Now let's cover tangent lines. Here we have this curve. I'm going to draw a tangent line right here. Let me do that again. So let's say I want this point right here. A tangent line touches a curve at exactly one point and doesn't cross. Now, there's something useful about tangent lines, and it's that the slope of this tangent line is equal to the slope of the curve at this point. And so we can use this property to actually find tangent lines. The easiest way to write tangent lines is the point slope form, because we can have a point and our slope. Remember that point slope form looks like this. We have your x1, y1 as your point, and m is your slope. We can rewrite this, make this more useful for calculus. The f of x, I'll write a. F of a is your y value of the point. F prime of a is your slope, and you have x minus a, and that a is your x value. I'm using a as a placeholder, but you'll see that we replace this a with whatever value the problem gives us. So here's one sample tangent line problem. I'm going to quickly write down the formula to make this easier. This is the format of your tangent line. You need to fill in these parts in order to make an equation. So find the line tangent to x squared plus 3x at x equals 1. It gives us our x value here, and that is what we'll use for our a, so that 1 will go right here. Now we just need to find f of a and f prime of a. Let's find f of a first. And since our a is 1, that's f of 1. Since it's just f of 1, what you do is you plug 1 into the equation here, into the function 1 squared plus 3 times 1. That gives you 1 plus 3, which is 4. Your 4 is going to go in the spot right here. Now we just need to find f prime of a. Plugging a into the derivative function. First, we're going to find the derivative using the power rule. You have x squared. Take the 2, multiply it out, decrease it by 1, so you get x to the 1, which is just x, and you have 3x. The derivative of that is just 3. So now you have our derivative function 2x plus 3. We plug in our x value, 1, into the derivative function that we just found. So that's 2 plus 3 will get you 5. Now you have all the parts you need to make the tangent line. So the last thing you do is you plug them all in. F of a, we got that to be 4. F prime of a, that's 5. And the a value which it gave us was 1. This is the answer. This is the tangent line to x squared plus 3x at x equals 1. Let's do another one. Find the line tangent to 2x cubed minus x plus 4 at x equals 0. First I'm going to find is f of 0. So you plug 0 into the function here. 0 minus 0 plus 4. You have 4 for that. Now let's find our derivative. We're going to use the power rule. Take the 2x cubed, multiply this out, so you have 6x, decrease it by 1, so it's 6x squared, minus x, goes to minus 1, and then plus 4, that's a constant, and the derivative of any constant, or any number, is just 0, so we're going to leave this out. So you have 6x squared minus 1. Now let's find f prime of 0 by plugging 0 into the function that we found. That's 0 minus 1, you get negative 1. Now we have everything we need for the tangent line. We start with y minus 4, our f of a, equals, we're going to put the slope, negative 1, times x minus 0. And of course you can simplify this. X minus 0 is just x, and then negative 1x. You just get negative x here. And this would be your answer. You may also find that some tangent lines may be converted to y equals mx plus b form, where you have to solve for y, you just add 4 to both sides. And that's another answer you could have. Many multiple choice questions may have the y equals mx plus b form, or the point slope form, depends. The last topic is second derivatives. The derivatives we've been taking are called first derivatives, and that's your dy over dx, your f prime, that stuff. The second derivative is the derivative of the first derivative. And there are many ways to write this. I find as f double prime of x, where you have 2 ticks, d squared y over dx squared. The exponents for the derivatives will go after the d on the top and after the x on the bottom, or whatever independent variable we have. You also find it written like this. We have the second derivative of a function. You may also find it as y double prime. And here it's asking us to find the second derivative of 3x to the 4 minus 5x squared plus 2x minus 7. To find the second derivative, we have to find the first derivative first. So let's do that right now. We're going to use the power rule to multiply this out. 4 times 3 is 12. Decrease that by 1, you get 3. Minus, same thing here, multiply it out, you get 10x, and plus 2x, that turns into plus 2, and then minus 7, you leave that out of the derivative, because there's no x, it's just a constant. So now you have our first derivative right here. To find the second derivative, we take the derivative of this first derivative function right here. take 3, multiply it out, get 36x squared minus 10, and plus 2, you leave that out. So the second derivative of this function is 36x squared minus 10